If I were to talk to any random group of Java developers and ask who's happy with ZGC, with virtual threads, with FFM, with JFR, performance improvements, etc., I think almost everyone would say they're happy. Maybe not with every detail, but they'd generally be happy. But some features involve trade-offs that require some people to give something up. Such trade-offs may be controversial because understanding their nuances requires special expertise, or they require people to take a broader view, that of the entire ecosystem, not just their personal needs. Brian Getz sometimes calls these two kinds of features jetpacks versus seatbelts. The purpose of this talk is to describe the idea behind some of these seatbelts and explain how they create value. As we'll see, integrity is, at least in part, the answer to the most serious and costly problems that software developers face. But before even explaining what integrity is, let us begin with the motivation, how things that have changed in recent memory made seatbelts so much more valuable than before. Java's backward compatibility has been a great success, even though it's not perfect. In fact, I would say it is unmatched by any other programming language when you consider the size of the ecosystem. The Java platform has always maintained its backward compatibility through the Java SE specification, but the careful process of evolving the spec is also applied to what we call supported JDK-specific APIs that don't begin with the Java namespace. The JDK's development has a deep-rooted culture designed to preserve compatibility, and we have a whole process called CSR to track all source, binary, and behavioral compatibility issues. This isn't just a principle we follow, but a primary source of Java's value. Companies want to protect their investment, and that means two things. Existing code continues working, and there's no waste and rework that produces little or no business value. But at the same time, they need the platform to evolve to support their changing needs and new computing capabilities. That's nice and all, but it's easier said than done. In Java's first decade, like in the first decade of most successful programming languages, maintaining backward compatibility was easy. At first, the platform was small, and you just add stuff, remove nothing, everyone's happy. Then, due to business-related events, Java's evolution slowed down rather dramatically for some years. And then came Java 8, which was a tremendous success, but the pace of evolution hadn't yet picked up to its required level. Now, pretty much from Java's birth, some libraries bypassed the standard APIs and reached for internal JDK packages, classes, methods, and fields. They did it to offer new functionality that was missing from the JDK, from the standard APIs, to work around bugs, and to offer better performance for their functionality that they couldn't achieve with the standard APIs. The libraries that did that, and it was primarily libraries, not so much applications, maybe weren't numerous, but they were very popular, sometimes as low-level dependencies of other libraries. Still, that work meant and was technical debt. The ecosystem was borrowing against its future. But it worked for a while. In the early years, we didn't have the foresight to add strong encapsulation, a way to hide the JDK's internals. And the response to libraries reaching for internals was to take extra care when changing internals. And basically, we have a contract. If you're using internals, that means that you accept upon yourself to do more maintenance as a library because these things can change. But because we knew that quite a few important libraries were using internals, we also tried not to change those internals so much. And that approach slowed us down considerably. And then after a while, it didn't matter because Java experienced some slow years in which the JDK just didn't change at all, either internally or externally. And the result was that the ecosystem had ossified around a very specific internal structure of the JDK. The low-level libraries that reach into internals weren't portable. They made the high-level libraries that used them non-portable. And they, in turn, made a whole lot of applications that used them non-portable, usually without the knowledge of the application authors. A lot of applications use libraries that weren't portable, and the application didn't know that they were actually stuck on some version of the JDK. So one option was to give up on making any foundational changes forever and let the platform slowly wane. But that's not what happened. Then Java 9 came along and brought those modules thing that broke that entire tower of code when they blocked off access to JDK internals, and in particular to sunMISC and safe, right? Now, that's not what happened. Modules were indeed designed to eventually block off access to JDK internals, but that happened in JDK 16. All runtime access to internals between JDK 9 and JDK 16 remained exactly as it was in JDK 8. Modules could not have been the cause of some migration issues because they were essentially turned off until JDK 16. Also, unsaved wasn't removed. It's still with us to this day, just as accessible as it was in JDK 8, although that is now finally changing. What actually happened was that in JDK 9, Java finally started picking up the pace again. That was one of the biggest releases ever, probably the biggest. But by then, the structure of the ecosystem had become dependent not on Java's promise of backward compatibility through the standard APIs, but on the JDK's internal machinery, and dependent on them remaining largely frozen. And then the JDK came out of a relative hibernation. The only backward incompatible changes that the JDK made in version 9, in terms of promises, Java's backward compatibility promise through standard APIs, were minuscule. There were 4 virtually unused methods removed. All the migration difficulty from 8 to 9 or 11, which was very real and cost the industry a lot, was 99% or more due to low-level libraries reaching into JDK internals. So one of the biggest changes is that now Java is evolving quickly. Internals change frequently, and so reaching beyond the standard APIs to use internals doesn't work, or at least it doesn't work for very long. Whatever advantages it once brought are now negated by the rework required to keep up with the JDK's evolution. And again, the ecosystem spent a lot of money on that migration. A recent report estimates that the cost of technical debt is quite high. And in that case, which is no less important, the technical debt was taken by low-level libraries, and it was passed on to client applications without their knowledge. That maybe the functionality was worth it, but the applications didn't necessarily know they were making that deal. Another change is that more and more of the Java runtime is being written in Java. Legacy I/O functionality that used to be written in C was rewritten completely in Java as part of the work in virtual threads. Much of the reflection functionality that used to be implemented in the JVM has been re-implemented in Java in the core libraries. We now even have a thread scheduler that's written in Java. The Gradual project has produced a JIT compiler written in Java. And there have also been environmental changes coming from the outside. There are new environments for Java applications that bring their own requirements. For example, some Java servers want to scale to 0 and start up quickly at or near maximal performance, and Mark mentioned that as part of Project Leiden. Finally, the security focus has shifted from defending against untrusted, potentially malicious code running on the client, and that kind of code is actually relatively easy to defend against, especially these days of containers, to defending against vulnerabilities in trusted code. Most attacks on servers exploit accidental vulnerabilities in well-meaning trusted code, and well-meaning benevolent code is far more dangerous than trusted code, and defending against those vulnerabilities is more challenging. Now, there is one exception to that, which is malicious code through supply chain attacks. I'm certain this is something we will have to address, but we won't be talking about that today. And the value of security is absolutely massive. And as it turns out, there is a strong relationship between integrity and security, but they are definitely not the same. Microsoft says that about 70% of all security vulnerabilities in memory unsafe languages are due to a lack of memory safety. Memory safety is a kind of integrity. So now when I use that word, but I haven't explained what it is, let's see what is integrity and how is it related to these different problems and challenges and changes that I mentioned. So integrity is a promise that some property holds true. Let's define a couple of terms. An invariant is a property of a program that holds true throughout some section of code. That section of code could be the entire program or a single method, but we will mostly be talking about invariants that are meant to hold throughout the entire program. I will use the term integrity invariant to mean an invariant that doesn't just happen to be true, but one that is guaranteed to hold because it is enforced directly or indirectly by the language or the runtime. And that enforcement is a source of integrity. That is what allows making the promise that an invariant holds regardless of what code in the program does. For example, that no array is accessed outside of its bounds in Java, or in general, that should be an invariant in all C programs. But that property in C doesn't have integrity. It's not guaranteed. It needs to be true. I hope it's true. Sometimes it isn't. But it's not guaranteed. To know whether or not it holds would require a full program analysis, which is usually infeasible, and that is why too often this isn't an invariant in C programs, and unfortunately buffer overflows do occur. On the other hand, allocating a new array in Java at one point in the code promises and guarantees that the array will never be accessed outside of its bounds anywhere else in the code, because that invariant has integrity in the Java platform. So integrity allows establishing something locally, using local reasoning, that is then known to be in effect globally. Here are some other integrity invariants in the Java platform. Some of them are meant to guarantee that Java programs, unlike C or C++ programs, don't have undefined behavior. They include array bounds checking, no use after free. Those are guaranteed by Java's memory management. Java also has runtime type safety, where an object of one type cannot be cast into an unrelated one. This also avoids undefined behavior, but has even bigger consequences. These invariants are usually grouped under the umbrella of memory safety. But we also have other kinds of integrity invariants. For example, that all relative file paths always refer to the same files throughout the lifetime of the process. That is enforced by not providing a change current directory operation in the JDK. Sometimes people ask for it, but that is the reason why we don't have it, because we want that guarantee. When looking at these, it is clear how integrity has been such a crucial part of Java's proposition since the beginning, although it hasn't been given that name. Now, these integrity invariants are built into the platform, most of them into the VM, where they are enforced by C++ code. But is it possible for Java code, including user code, to establish new invariants that have integrity? Well, we can try. Suppose we want to write a class implementing an even counter of sorts. It has the invariant that the counter's value is always even. So we can try writing something like that. So we try to give the invariant integrity to ensure that it holds everywhere without analyzing all code in the program. by making the field storing the value private, and by having all the public methods preserve the invariants. In this way, if the encapsulation itself, Java's access control, has integrity, so will our new invariants. So the invariance of that x is always even depends on whether or not access control in Java has integrity. In fact, even the platform's primitive integrity invariants gain their strength from encapsulation. The code that enforces them is encapsulated from Java code by virtue of its being written in C++. And before we go further, let's take a short detour and talk about how a Java program is built, and Alex mentioned it before. So we have our application code, and then we're using a bunch of libraries, but those libraries bring their own library dependencies to form a rather large and deep dependency graph. We said before that an invariant has integrity if it is guaranteed to hold no matter what other code does. And we said that our even counter classes invariant has integrity if the Java platform's encapsulation has integrity. But does it? Sadly, no. Each one of those libraries in that deep dependency graph, so everyone here, including those that you may not even know about, can choose on its own unilaterally to violate Java's access control, and with it, the invariant of the even class. They can use what we call deep reflection, i.e. set accessible to set the value field, that x field, or they could easily do that before JDK 16, well, depending on whether you put the class in a module or not. They can also do that with sunMISC unsafe or with JNI. Or they could decide to dynamically load an agent that will redefine the class so that the increment by 2 methods actually increments by 3. And each of these mechanisms individually means that Java encapsulation doesn't have integrity, and so neither does our even counter class. To know whether any invariant that we want to maintain in Java code holds, we need to do a full program analysis, just as we need to do it for buffer overflows in C. And this matters even more now that more of the runtime is written in Java. So if we have a JIT that's written in Java, Java code could change the JIT to decide that we no longer enforce inbound array access. Now that we have a thread scheduler written in Java, Java code could change its operations so that the Java memory model will no longer work. But you say, surely the fact that some 4th level dependency could do that doesn't mean that it would, or would it? So to answer that, we'll need to understand why integrity invariants are important and how they get broken. So this is how we started. To evolve the platform at the required pace, we need to be able to fearlessly change all internal code that isn't and has never been subject to backward compatibility. And in this case, the answer to the question of why a library would want to violate other code's encapsulation is that they have various possibly good reasons, such as exposing new functionality, work around bugs, or improve performance. These reasons may be justified individually, but the result is a tragedy of the commons, and that was by far the main reason for the difficulties upgrading from 8. Libraries essentially took on technical debt and foisted it onto unsuspecting, unknowing applications. Encapsulating JDK internals with integrity so that some private constructor cannot be called by some library will mean that applications don't break again when that constructor is changed. And I think we see that, how easy it is to upgrade from JDK 27 to JDK 23, even though in that period of time, the JDK has changed much more than it did between 6 and 7, and even 7 and 8. Now, the Java ecosystem wouldn't be what it is without library authors. Their perspective makes complete sense. They do what they need to do to offer the best functionality they can to their users. It's just that their individual actions, when taken collectively, lead to a negative outcome globally. And that ends up wasting a lot of effort by people who may not be aware that they're taking on such technical debt. And that is why a tragedy of the commons is a tragedy. Every individual action is justifiable, and no individual action is to blame. Now, if you read about solutions to tragedies of the commons, I think that the only one that is practical in our situation is regulation. Somebody, certain body, is in charge of the common resource, and they place rules that they enforce. We can generalize the previous points to dependencies in general, right? So modern applications are composed of many components, and this works better when each of those components can trust its own invariants. But sometimes you want to work around bugs or around functionality. We have this sort of thing that you want to write your code as if nothing else can interfere with it, but someone else can say, okay, but sometimes I do want to interfere with it. We'll see how we do that later. Now let's take a look at security. Suppose that a server has this user session class, and it has some sensitive operation which it only allows to do after the user has been authorized. And the way we ensure that is that we only do the operation after checking that the user was authenticated. Now, one thing that's very important in all security mechanisms is that they must be robust, by which we mean that their operation must be correct regardless of what code in the rest of the application does. This allows us to treat them as independent code units whose correctness requires analyzing only a small amount of code. But no matter how sophisticated the authorization algorithm is, what kind of post-quantum cryptography it uses, if encapsulation has no integrity, the security mechanism is not robust. That field saying that the user has been authorized could be set, say, with J and I. That method, do sensitive operation, which is private, could also be called through J and I or deep reflection. That method that actually does a cryptographic authentication of the user could be replaced by a method that returns true by an agent. So if in the evolution case, we could see a reason for a library to violate encapsulation, surely in this case we think that no library would feel justified to circumvent a security mechanism. And remember, we're only talking about well-meaning libraries. We're not talking about malicious code. But the answer is that in this case, even if all code in the application and the libraries is well-intentioned, a malicious remote attacker who is interested in bypassing this security mechanism could manipulate good code to do just that. So imagine we have our application, and our application uses that session class. And it also employs a library called goodSerializer to deserialize JSON. Because it deserializes JSON, and it might want to deserialize and assign JSON fields to fields of Java objects that are final, it needs to use deep reflection. So it uses another library called neutral encapsulation breaker to instantiate objects without invoking their constructor and assign their private fields. Now there's a bug in goodSerializer sanitization. And through that, you can deserialize some specific JSON object that would deserialize to some arbitrary class. And you could send it an input that would reassign that superuser field. Now, who's at fault? The application is innocent, doing its best. The serialization library is well-intentioned, but it has a bug. Bugs do happen. The neutral encapsulation breaker is neutral. It has no vulnerability in it. And yet, in combination, they cause this problem. Any library that breaks encapsulation and any library that uses that library becomes part of the attack surface area of any code that relies on encapsulation for integrity. And every security mechanism at any level always relies on encapsulation. Now, the integrity of encapsulation is not in itself a security mechanism. In the case we've seen, security mechanism is built by the application or the server framework, uses some cryptographic library in charge of the authentication. But if encapsulation had integrity, we would be reducing the attack surface area of the session class to some fixed unit of code that is small enough to analyze in isolation. Without that encapsulation, it doesn't matter how good the session class is, how strong the cryptographic algorithm is. All code that's part of that surface area, we would need to analyze. So you might need to, some clever people might ask, hang on, you don't need to actually bust encapsulation to break the session class. What if some library writes to the file system and there is a vulnerability somewhere that causes that library to write a new class file to the file system, and a remote attacker could manipulate it to change the what is called the session class on disk? Should we do something about it? Why don't we care about it? The answer is we do care. We absolutely should do something about it. It is just that the integrity of the file system is not the responsibility of the Java runtime. Every component of a system is in charge of its own integrity. And in that case, it's the responsibility of the OS to provide that required level of integrity, and you should make use of it. Finally, integrity is also important for performance, especially in light of the new requirements I mentioned at the beginning of scaling to 0. Sometimes we might want to, Mark mentioned, shifting computation to run before the program starts. So we need to know that nothing in the program has changed. I think Mark also mentioned that the JVM can't constant fold, which is an important optimization final fields, because we can't trust that they're actually final. And you don't actually need to make use, to use strong encapsulation or unsafe or something to lose that optimization ability of the JVM. The mere fact that these things could be used, even if you don't use them, means that the JVM is not allowed to optimize these things for anyone. Like every Java program in the world suffers, its performance suffers because some people in some other program might want to use deep reflection. So we've seen that encapsulation is broken in ways that have significant consequences, either because of individually justified reasons that lead to tragedy of the commons, or unintentionally due to an accidental vulnerability. And in some cases, it doesn't matter when it comes to performance. It doesn't matter what the reason is. Mechanical optimizations require absolute certainty that invariants are kept. The high probability that they're kept is not good enough. So we get this tension where we absolutely need integrity to offer some very important value, but we also sometimes need to break it in case of emergency. So what is the right balance to strike here? That balance is a vision that we have for the Java platform, and we've been working towards it for years, which we call integrity by default. Integrity by default seeks to strengthen the integrity of the Java platform, but it also recognizes that there are situations where people need to opt out of integrity. Therefore, the principle of integrity by default is this: all the exceptions to integrity must be explicitly acknowledged by the application in its centralized configuration. The important point here is that the decision is given to the application. As we've seen, lack of integrity causes a collapse of barriers of sorts where code can affect other code remotely, and the decision whether or not to allow this is given to whoever's in charge of the entire program and not the library dependencies. If a library really wants to break encapsulation for some reason, the application needs to grant it permission, usually by adding some configuration flag. This means that fourth level dependencies will not be able to unilaterally make the application non-portable and perhaps even risk its security without the application's knowledge and consent. You're allowed to do this, but you can't do this without your client application knowing. Now, what matters isn't so much how the configuration is constructed. Some people will say, well, okay, a library will say, I need to break encapsulation and add something to its POM file, and Maven will automatically add it to the configuration. And if so, what's the point? That is fine. No matter who creates a configuration, in the end, there must be some runtime configuration in the form of an at file or a command line flags that is auditable. And it's a centralized record that some technical authority in a company can look and see what risks, maintainability risk, portability risk, or even security risks, or performance risk, the application has decided to take upon itself. So I hope that by now we understand why integrity is important, but you may ask a reasonable question, which is, given that Java didn't start out with strong encapsulation, why not make it opt-in rather than opt-out? The first part of the answer is that we choose opt-out because we can. Strong encapsulation was designed so that its boundaries have a reasonable granularity, and so are simple to configure. The level of a class was too small, the level of a package was too small, but the level of a module, you don't have that many modules, so it's easy to configure. Most programs can work with a default policy, 0 flags, or something close to it, and then they enjoy the portability and the other benefits more easily than ever. Those that don't will be inconvenienced. You do need to add flags, but not too much. The second part is that the two regimes, one with strong encapsulation and one without it, are not symmetrical. The strong encapsulation regime has lower entropy in a very strong sense. There are fewer hypothetical programs that work in that regime because it can do less. When you write a new program, it's best to start in the low entropy regime. And if you have an old code base, you have to expend energy only once to get to low energy. And then you put the barriers in place, you're now in low entropy, and entropy can't creep in, at least not unnoticed. So as we've seen, the integrity of encapsulation is of particular importance because encapsulation is what gives Java code the ability to create its own invariants. And I've used that term before, but now defining it is called strong encapsulation. It is not 100% complete yet, but it will eventually ensure that code in one module will not be able to reach into encapsulated components in another module using any of the means I mentioned before. That includes JNI, unsafe, whatever, unless the declaring module explicitly allows it in its module declaration. Code passes its access permission to other code via method handles lookup. I think not enough people know about this, but read about this. Any code that has certain abilities to reach into other modules can very easily pass those permissions to any other code. Or the application redraws the encapsulation border with command line flags. Or the application grants some encapsulation breaking superpowers by loading an agent and specifying an agent on the command line, or using JNI. The most obvious impact that applications feel in the real world is that if they upgrade their JDK from, say, JDK 8 to 17, or from 11 to 17, they may need to add some add opens and or add export flags. Some people make the crucial mistake that these flags are sort of a JDK 8 compatibility mode that allows our application to continue working as it did on 8. Nothing can be further from the truth. The flags cannot possibly make the application work because internal changes will break it. The reason things break is not because we stop access to them. Remember, we only did that in 16. They break because the JDK is now changing. An application that uses those flags is an application that will break. And the more flags, the sooner it will break. So what's the point of those flags? The flags are like landmine markers. They keep you alive while you clear the landmines. Reaching for internals, that is the problem. That's a landmine, not the flag. The only fix is to stop relying on internals. And the flags might give you some time before you blow up. Complaining about the flags is like someone who wants to throw a party in a minefield, and they complain that the minefield markers are an eyesore. Now, it may be ironic that rather than the application breaking in some future release, recent JDKs break it with certainty, because when we block access, things break with an exception. But the key is that we only break it once. That's it. And we break it in a way that ensures that the only fix is to remove the reliance on internals. Once that's done and there are no more flags, the library is portable forever, as it's now protected by our backward compatibility process. Without this, the 8 to 9 migration pain would continue forever and ever. Going from JDK 17 to 23 would have been the same or harder than going from 8 to 9. A library will fix a change internal. Without those flags, a library, let's say we change an internal, a library would break, an application would break, so the library would just depend on another internal. With strong encapsulation, we can ensure that we eventually converge, or at least we can notice if we don't. So such flags are for temporary use, but if you need a flag to keep some library working and there's no new version of the library that doesn't require the flag, well, that is a big red flag over the library itself. It means it might not be properly maintained, and maybe look for alternatives, and that's another benefit. By the way, I know of a project that only realized it was dependent on a library that hadn't been maintained for years, because they saw that they had to add an add opens flag, and then they asked why, and then they noticed they're using a defunct library. So some people say, well, from your ivory tower, you can just decree that everyone should fix the technical debt, but in the real world, companies don't have the resources to do it, or don't want to direct the resources toward paying the technical debt. This is perfectly true, but the fact that the developer may not be offered a choice to reduce risk doesn't mean that the risks go away. Sure, some places can't fix their bridges, but from time to time, their bridges do collapse. If you don't upgrade libraries and remove the dependence on JDK internals, the risk that the application will break when the JDK is updated is real. So it's best to at least know it's there, even if you can't do anything about it. It's not like if you don't know it's there, it doesn't go away. So I would suggest that if you do add opens and add export flags, you at least document why, either in the comments, in the startup script, or in the Git commit that introduced the flag, so just so that you remember. Now, there are situations that, by their nature, they're required to operate beyond encapsulation. They have to do with unit tests, various code, dependency injection frameworks, APM tools, serializations. In the integrity by default project, we have guidance on how those libraries should operate, but there are solutions for all of them. How much time do I have? So far, I talked about strong encapsulation, but we're also restricting some aspects of new APIs such as FFM, the new foreign function memory API, even though it cannot be used to break Java encapsulation. However, it can lead, because it can call C code, it can lead to undefined behavior, either by calling into code written in a memory unsafe language, or by manipulating off-heap memory in arbitrary ways. This is an excerpt from a recent information sheet by the NSA about memory safety, which is a kind of integrity invariant. And the paper emphasizes the risk of memory unsafety, and it says that these operations should be localized to identifiable units of code, so you know where they happened, so that those units could be scrutinized. And the paper further says that this kind of safety sometimes places onerous work on the developer, but in Java that is not quite the case. Most Java programs don't need memory unsafe operations at all, and those that do, it's quite easy to add a flag that will tell you where the problem is. Achieving integrity by default is being done in stages. So we started restricting deep reflection since JDK 16. We recently, I can't remember, maybe JDK 21, started issuing a warning when you try to load an agent dynamically, not through the command line. FFM start out restricted, and JNI is now restricted as of today, and unsafe will be removed. As always, for all of these, there's a gradual process that will give people enough time to adapt, and this is how it works. Whenever we say something is restricted in support of integrity by default, and so if we restrict some operation that was previously unrestricted, for example, using JNI, we follow this process. So first we say there's a flag that grants this access to a certain module. In this case, enable native access. This is you saying this module is allowed to use JNI. But you don't have to start with identifying those modules. There is sort of a global flag that says what happens if you don't enable native access. In this case, that flag is called illegal native access, and it has like a knob or a dial that will gradually react more forcefully. So at first, it might be that the operation is allowed. We normally start with a warning. So with JNI, when you use JNI, by default, you get a warning unless you enable native access or you set the legal native access flag by default. Then at some point, legal native access or some other flags like it will default to deny. When we change the flag to deny, you could go back to warn, but not back to allow. You could go back one grade. And in the future, the flag will go away and deny will be the only option. There are various steps that we start doing this. I mentioned agents, JNI. We're starting to remove the message in some misc unsafe also gradually and with warnings. And there's more to follow, especially around making finals trustable. And with that, I am done. Thank you. I don't think we have much time for questions, but maybe one or two.
Just a quick one. Do you expect one day that it's like completely going to be gone, no more opt-in at all? I guess you kind of mentioned that at the end there.
Maybe not. I don't know. I think there's power in saying sometimes you have to work around something. But as long as you, the application owner, knows what is being busted open, I think that's okay. So I don't see immediate need to remove it.
You had mentioned something about FFM having restricted calls in current code in the future. Is there a protection scheme for the foreign code having the ability to call into the JDK code? And is that kind of going through more of a insulation shield than the JNI equivalent would have?
No. The way it works is that the Java code that uses the API, foreign code can't call into Java using FFM without Java calling it first. Okay. So you need to allow Java to call it, and then by extension, it can call into Java. It can't call, it doesn't work like JNI. It can't call arbitrary Java methods. It can call callbacks that you give it. It works in a different way. So it's not, its operation is much more restricted.
Thank you.
One more.
About the removal of the security manager, does it not in a way go against the intention of the integrity by default? I do understand that security manager is there to protect access to the local resources, but can it not be leveraged for this purpose as well?
So you're asking what doesn't go against?
The removal of the security manager.
No,
yeah.
Because security manager was pretty bad at offering integrity. When integrity was and security. That's the main. It's removed because it doesn't offer security. It offers security for the people who manage to configure it correctly. The people who try are a vanishingly small portion. The people who succeed are almost no one, and that is because it wasn't designed for the kind of dependency complexity that we have today. So it's being removed because it doesn't accomplish its purpose. Okay, and I think that's time, so thank you.